stated without proof during the lecture, we are asked to prove that 5-fold rotational symmetry is not consistent with translation symmetry in a perfectly periodic crystal. In order to prove this, suppose we consider an n-fold rotation axis perpendicular to the plane of the board. Let us for example consider a 4-fold n equal to 4. Figure 1a shows such a 4-fold rotation, a 4-fold symmetry axis in a translational invariant crystal lattice. So, one has atoms in these various lattice positions, and this angle, the angle is 90 degrees for n equal to 4. So, this is also the case here, and this is the lattice translation vector. So, this rotation axis takes it to this position, and the rotation axis, 4-fold rotation axis, takes this to this position, and now the final position of these two atoms should also be consistent with the translational symmetry of the lattice. Similarly, the next figure 1b also shows the same thing for n equal to 6 for a 120 degree rotation. Now, in general we can show this in 1-2c, the general situation is shown, from which it is clear that we have the condition t minus 2t cos alpha should be some integer times the translation vector. T is the translation component in the translational periodicity of the lattice, and alpha is the angle through the rotation axis. So, that would be the condition that has to be satisfied, which becomes therefore, which gives cos alpha equals 1 minus m by 2, where m is an integer. Since it is an integer, we can also write it as some other integer by 2. And so, the table shows the various values, since cos alpha cannot exceed minus 1 or plus 1. So, that imposes a restriction on the allowed values of m and hence the small m. Therefore, the rotational, the alpha values which correspond to an integer m in this condition are given in tabular form. So, from that it is clear that n equal to either 1 or 2 or 3 or 4 or 6, and a 5-fold rotation is therefore not consistent with the translation periodicity. The next problem talks about a 2-dimensional matrix representation of twofold, threefold, fourfold and sixfold axis of rotation, namely the group C2, C3, C4 and C6. So, if you have rotation corresponding to these axes, how do you represent them matrix in matrix form? This is important for a group theoretical understanding of the characters and represent basis of these point groups. Suppose we consider C2, the Schwanflies symbol is C2 and the international symbol is 2, and the matrix element, since the angle of the rotation is pi. So, we have in general cos alpha minus sin alpha, cos alpha. In 3 dimensions it is, this is the matrix representation of a rotation axis about which coincides along the z axis. Now, the basis for this is the coordinates x, y, z in 3 dimensional space. Now, we are asked to provide 2 dimensional representations. So, that will be for a twofold axis, it will be cos pi minus sin pi, cos pi, which is cos pi is minus 1, this is 0, this is 0, this is also minus 1, provided we deal with these, which means that this is the basis. The basis for this is x, y. That is one 2 dimensional representation. Of course, one can choose y z or x z as the basis. Suppose I choose x z as the basis x z, then the corresponding matrix elements are cos alpha 1 0 0 for alpha equal to pi. So, the matrix representation is minus 1 0 0 1. This is also an equally valid representation of the C2 axis for if the basis adopted is x z. Alternatively, we can also have basis y z. If that is the case, then we have cos alpha 0 0 1. So, that is again the same matrix for both these. So, we have the possibility of 2 different representations depending on whether we choose x y as the basis or x z or y z as the basis. Depending on that, these provide the 2 different representations for the C2 rotation. Now, since it is of this form, we can of course factor it further, partition the matrix further, and the corresponding basis can be 1 dimensional. So, x or y. So, this is a completely reducible basis, it is a reducible representation. It can be the 2 dimensional representation can be reduced into 2 1 dimensional representation. Similarly, these also can be reduced. So, this is also reducible. Now, we proceed to a C3 axis. For the C3 axis, the cosine alpha, alpha is 2 pi by 3. So, I have cos 2 pi by 3 minus sin 2 pi by 3 0 sin 2 pi by 3 cos 2 pi by 3 0 0 0 1 is the 3 dimensional full 3 dimensional representation with the basis x y z. So, this can be written as minus half minus root 3 by 2 and root 3 by 2 0 0 1 0 0. So, we have the possibility depending on which representations we choose, we can partition this matrix like this. So, this can be a 1 2 dimensional representation for the C3 rotation z axis. So, it can be minus half minus root 3 by 2 root 3 by 2 minus half. That would be a two dimensional representation for the basis x y. Or if we choose x z as the basis, then that would be minus root minus half 0 0 1. That would be for the basis x z, or it can be y z can be the basis. So, these are the three two dimensional representations, and we can see that this is reducible. This is also reducible, since the off diagonal matrix elements are all zeros. So, these both these are reducible, whereas going on to the case of the C4 axis, a fourfold rotation by the z axis. So, it has cos pi by 2 C4 cos pi by 2 minus sin pi by 2 sin pi by 2 cos pi by 2 0 0 1. That is the three dimensional representation with x, y and z, and that would correspond to cos pi by 2 is 0 and minus 1 1 0 0 0 0 1. So, the corresponding two dimensional representations for the C4 axis will be 0 minus 1 1 0 if we choose x y as the basis, whereas it will be 0 0 0 1 if it is x z. Y z will be yeah also. Obviously, this is a reducible representation, while this is not. Coming to the C6 axis, by the same reasoning one can arrive at the answers. So, we have cos 0 0 1 for the y z basis also. So, that answers the question. We now pass on to problem 3 and 4, which are taken together. We are required to construct the character table for the following point groups. The first point group to be considered is 2 by m, which is a mirror perpendicular to a twofold axis. So, it goes by the nomenclature C2H in Schoenflies notation. So, C2H has the elements, these are the elements, a C2 square is I, and because there is a mirror sigma h, and that produces an inversion symmetry. So, there are 4 elements in this group, and therefore, there are 4 irreducible representations. The number of irreducible representations is equal to number of classes really. There are 4 different classes now, 1, 2, 3, 4. So, since there are 4 elements, so one is the totally symmetric representation, and then you can have and that is called G because of the inversion symmetry. G is Gerade. So, it is symmetric with respect to the inversion. There is also another one dimensional representation Bg, and then you have an Ungerade, which is odd with respect to inversion, and Bu. So, this will have 1 1 1 1 and this will have 1 1 minus 1 minus 1, this will have 1 1 minus 1 minus 1 B minus 1. So, that would be the character table for the group 2 by M or C2H. We now pass on to the next point group and proceed to construct the character table. The next point group which we take up is 4 to 2, it is D4. So, these are two C4s and a C2 which is C4 square. And then you have the additional twofold axis 2 C2 and C2 double dash. So, there are 5 classes and therefore, 5 irreducible representations which are A1, A2, B1, B2 and then E, a 2 dimensional representation. So, the characters are, this is totally symmetric of course, and then this will be antisymmetric with respect to this axis. So, you have B1 which has antisymmetry with respect to this axis, and another one, and then you have 2 dimensional representations which has the character 2 for the identity, it has the character 0 as we saw already, this will be minus 2 0 0. So, that would be the character table for D4. We next pass on to the tetrahedral group, which is one of the cubic point groups O, the group O, which is the octahedral group, which is also a cubic point group. Now, if we consider the pure rotation axis, the elements are identity, and then you have 6 C4, 3 C2, then 8 C3 and 3 C2 dash. So, you have 1 plus 6 7 plus 3 10 18 and 6 18 plus 6 24. Because of this you will have 5 irreducible representations. So, these will be A1 1 dimensional, A2 E T1 2 dimensional and 3 dimensional here. So, this will have the characters 1 1 1 1 and then you will have 1 minus 1 1 1 minus 1, then you will have 2 0 2 0 2 to satisfy orthogonality, and the 3 dimensional rotation representations will have 3 1 minus 1 and then 0 minus 1. And the other irreducible representation will have -1 here. So, these are the various irreducible representations of the, and the next problem concerns the short flies notations, which are also given already here. We now pass on to the next problem, which concerns the space group notations. So, problem is on space groups. We are given the symbols for the different space groups. We have P21 by C. As we already explained during the lecture, the P stands for a primitive crystal lattice with one atom in the unit cell, and the isogonal point group is 2 by m is the point group symmetry of the space group, which means that it is a monoclinic crystal lattice. The Breve lattice is a monoclinic primitive, and you have a 2-1 screw instead of a pure 2-fold axis, which means that there is a twofold axis followed by a translation component, which is b by 2, half the translation along the b axis. And the symbol C means that instead of the pure mirror symmetry, we have a glide plane in the plane perpendicular to this b axis. So, with a translation component C by 2 along the C axis. So, we have a mirror plane, which is the AC plane, and it is a mirror plane with a translation component of C by 2 along the C axis. So, that is the explanation. The next space group to be considered is R3 bar M. So, the symbol R stands for a rhombohedral crystal lattice, which belongs to a trigonal point group, trigonal crystal system with a point group symmetry of 3 bar m. So, this is what is called D3D in Schonflies notation. So, the 3 bar m means that there is a roto inversion axis. 3 bar is a roto inversion along the z, along the c axis, and then you have vertical mirror planes pure mirror planes with no translation components coinciding with the roto inversion axis. So, that is the symmetry. The next space group to be considered is FDD2. So, the symbol F means it is a face centered lattice. The Breve lattice is a face centered lattice, and since D corresponds to mirror symmetry, so it is MM2 is the point group, which is also known as the C2V. This is the point group symmetry. So, that means that this is an orthorhombic since we have mirrors along the A and B planes perpendicular to the A and B axis and a twofold axis in the along the Z, and the symbol D means these are not pure mirror symmetries, but diamond glides with the translation components. So, this is the first one is A perpendicular to the A axis. So, the BC plane, and this one is perpendicular to the B axis. So, AC plane. So, the components are A plus C by 4. In this plane, in these two planes, and you have a pure twofold axis. Next we move on to the space group symbol. For 1 or A C D with an I in front. So, the symbol I stands for body centered lattice, and the symbol 4-1 means the isogonal point group is 4 by, these are all mirrors. So, this is the point group 4 by mm. So, fourfold axis with vertical. So, this is D4H, and so it is a tetragonal crystal system because we have a unique to fourfold axis. And the interesting thing is that we have not just a fourfold axis, but a 4-1 screw with a translation component of this along C axis. So, the translation component is C by 4. That is the translation component, and we have A glide and then C glide in the plane perpendicular to the B axis, which is the AC plane. So, this again C by 2, and we have also a diamond glide in the BC. So, there are 3 glide planes in all the principal crystallographic planes with translation components of A by 2, C by 2 and A plus B by 4 respectively. Lastly, we take the case FD3C. The symbol F obviously refers to a face centered lattice, and D3C means it is M, the point group is M3M, and that is nothing but TH, the tetrahedral cubic point group. So, it is a cubic crystal, it is a body centered cubic Breve lattice with an isogonal point group M3M or TH. And we have a diamond glide. So, instead of the pure mirror plane, it is a diamond glide. This is a pure threefold axis and a C glide. Corresponding to this. So, the diamond glide means it is A plus B by 4 and the C glide is the translation component is C by 2. And this is in the BC plane and this is the diamond glide in the AB plane. So, that explains the space group symbol of the space group FD3C, which is the cubic space group. The next problem is to determine the direction normal to the HKL plane in a cubic crystal. Figure 2 shows the plane ABC, which has the intercepts OA, OB and OC on the crystallographic axis, A axis, B axis and C axis respectively. So, OA, OB and OC are the intercepts. The Miller indices of this plane ABC are chosen to be HKL, so that by the definition of the Miller indices, OA is A by H, OB is B by H, B by K. Well, it is a cubic crystal, so it is all A by K, OC is A by L. Now, in the figure, let ON be the normal to the HKL plane. So, this length ON, let it be chosen as P. If that is so, the normal form of the equation to a plane at a distance P from the origin is given by, it is well known that it is given by x cosine alpha plus y cosine beta plus z cosine gamma equals P, where alpha, beta, gamma are the direction cosines of the normal. So, this is a standard result in coordinate geometry. So, we will use this. So, now therefore, we can write the coordinates of the point n. What are the coordinates of point n? They are p cos alpha, because the length ON is p. So, it is p cos alpha, p cos beta and p cos gamma. These are the coordinates of the point n. So, now referring to the figure, the ONA, the triangle ONA is a right angle triangle, and with cos alpha, which is ON by OA, and ON is P, and therefore, OA is A by H. Therefore, this is PH by A. Similarly, cos beta is PK by A, and cos gamma is PL by A. So, that the coordinates, these coordinates become, substituting for cos alpha, cos beta and cos gamma, we get P square H by A, P square K by A and P square L by A. Therefore, reducing this to the smallest integers and taking the common factors away, we arrive at h k l as direction normal to the plane h k l plane. So, that is the direction h k l. The next problem is to find the Miller indices of a plane which intercepts the crystallographic A and B axis are 0.25a, 0.25a and 0.5b, and it is also parallel to C axis. This is the plane, and therefore, we are asked to find the Miller indices. For Miller indices, we go from the intercepts by taking the reciprocals of the intercepts. The reciprocals are this is 1 by 4. So, it is 4 of course, by A and 2 by B, and then since it is parallel to C axis, the reciprocal is 0 because this is parallel. So, the intercept is infinity. Therefore, the reciprocal of infinity is 0. Therefore, this becomes 4 2 0, and therefore, no, we need not write A and B since they are measured in units of A and B. So, this is 4 2 and 0, which reduced to smallest integers is 2 1 0. Those are the Miller indices of the plane. Proceeding in the same way, we are also asked to find the Miller indices of phase diagonal in an FCC lattice. So, in an FCC lattice, the phase diagonal looks like this. So, the phase diagonal, for example, is like this, one of the phase diagonals. So, the plane containing the phase diagonals makes intercepts, its Miller indices are given by, it makes intercepts 1 and 1 on these axes, and it is parallel to this z axis. Therefore, the Miller indices are obviously 1 1 0. Now, not only 1 1 0, but also there are 12 phase diagonals. And the different planes which contain these phase diagonals are all the entire set of family of planes 1 1 0, 1 0 1, 0 1 1, also 1 bar 1 0 and so on. All of them, there are 12 of them, all of them belong to the same family of planes. The next problem is in the form of a table in which we are given different structures and we are asked to fill in the blanks for a table which gives the structure, the ratio between A, B and C, the value of alpha, beta and gamma and the number of atoms per unit cell. There are several blanks and the next table gives the answers with the missing entries which are filled in the blanks which are filled. So, the answers are obvious. So, I do not provide any explanation, the table is self explanatory. The next problem, we are asked to determine the ratio of the lattice constants. C and A. So, in other words, we are asked to determine C by A ratio for a HCP, hexagonal closed packed structure. The next figure shows the positions of 4 atoms in the HCP structure. Now, you have P, which is the position of the atom at the center or the top in the unit cell, the topmost point in the unit cell, which corresponds to one point in the unit cell. And the next layer, there are 3 corresponding positions of the atoms in the middle layer. They are written as Q, R and S. Now, by geometry you can see that the sides P R and R S are the sides of the unit cell and that is given by A, and therefore, since the angle is an equilateral triangle in QRS, therefore, the side R n is root 3 by 2 A and the O R is 2/3 of that, because O is the centroid of that. So, it divide the R n is divided in the ratio 1:2. Therefore, we have R O in the figure as 2/3 of root 3 by 2 A, which is A by root 3. So, that is the perpendicular distance R O from that is the distance R O, and we are required to find P O, the distance P O, which in the right angle triangle we have one side is A, another is what we found just now as A by root 3. So, the distance P O is square root of A square minus A square by 3, which is root 2 by 3 A. That is the distance from the top layer atom P to the centroid in the next lower layer. So, the actual C axis ratio is twice C is 2 times P O, and therefore, it is 2 root 2 by 3 . And therefore, the C by A ratio is 2 root 2 by root 3. That can also be written as root of 8 by 3, and that works out to 1.633. So, that is the ratio of the C to the A axis lattice parameters in the HCP structure. Next problem talks about atoms which are treated as rigid spheres, and then we are asked to calculate the fraction of space filled by atoms in different structures. This fraction is usually known as packing fraction. In short, it can be written as PF. For the simple cubic structure, for the face centered cubic structure, for the hexagonal close packed structure, and for the diamond structure. We proceed as follows. Let us consider the simple cubic, the simplest. In the simple cubic lattice, we know there is one atom per unit cell. So, if R is the atomic radius, then the volume occupied by the atoms in the unit cell this is simply the atom volume 4 pi r cube by 3, since there is only one atom. Whereas, the volume of the unit cell itself depends on the size of the unit cell. So, that will be the side of the unit cell has a distance 2r, where r is the atomic radius. So, the volume will be 2r cube, it is a cube of side 2r. So, the packing fraction is the ratio of the two. So, it will be on calculation, this will be pi by 6. Next, we consider Bcc structure. For the Bcc, there are two atoms, one at the body center and one at the corners, 2 atoms per unit cell. Therefore, the volume occupied by atoms equals 2 into 4 pi r cube by 3. Whereas, the unit cell volume now, we already saw the unit cell is 4r by root 3. So, that is the side. So, the packing fraction, which is the ratio of the two, is just root 3 pi by 8. Next, we consider the FCC structure, face centered cubic structure, where the number of atoms per unit cell is 4. So, the volume occupied by atoms in the unit cell is 4 times 4 pi r cube by 3. And the volume of the unit cell is 2 root 2 r. This is the side cube of this. So, the packing fraction is pi into root 2 by 6. We will talk about the diamond lattice. which is a special lattice. The diamond cell has carbon atoms at the vertex and at the along the body diagonal at 1/4, the 1/4, 1/4, 1/4 are the coordinates of the carbon atoms and so on, all the equivalent of these. So, there are in total number of atoms in unit cell is 8, as one can readily verify. So, the volume occupied by atoms in unit cell is 8 times 4 pi r cube by 3, whereas the volume of the unit cell itself is 8 r by root 3 cube, as one can readily see. So, the packing fraction in this case works out to be pi root 3 by 16, a rather small number. So, this is not a very close packed structure, the diamond is a rather open structure. That is because of the essential nature of the covalent bonding between the carbon atoms.